interpreting ternary phase diagrams. And this part is the isothermal section. So here we go. And when you're looking at any phase diagram, ternary, binary, whatever, we often use the Greek alphabet, the small letters, these letters, to denote solid phases. So it's well worthwhile learning them and knowing them. Here's the phase rule, and basically the full phase rule is P plus F equals C plus do, but metallurgical phase diagrams, we can get away with P plus F equals C plus 1, okay? And that's because we're really only interested in atmospheric pressure, and we're really only looking at the liquid phase just above where it solidifies. We're not interested when it vaporizes. And if it does that, it gets more complicated. So for us, we use the reduced or the condensed phase rule. P is the number of phases, F is the degree of freedom, and C is the number of components. So on a binary phase diagram, here's a eutectic, and I'm assuming that you're familiar with this. The phase rule will tell us that where you've got 3 phases, it's an invariant reaction. There's no degree of freedom, so therefore it's a straight line. So in this phase diagram, this eutectic reaction of liquid going of that composition going to form alpha of that composition and beta of that composition is an invariant reaction and will always occur with these compositions and at that temperature, the temperature of the eutectic. So binaries have got 2 components, ternaries have got 3 components. That means they're more complicated. And with binaries, it's easy to view on the paper or the screen. Ternaries, because it's a 3-dimensional, because you've now got 3 components in there, it's much less easy to view. So we need sections or projections. So we need to learn about those. Okay, and that's what this lecture is about, is an isothermal section. So on a binary, you've got single or 2-phase regions. On a ternary, you've got single, 2-phase, or 3-phase regions. We've just looked at the fact that the phase rule tells us in a binary, 3 phases are in an invariant reaction, so they're on a horizontal straight line. In a ternary, because you've got 1 more component, you've got 1 more degree of freedom, what actually happens is you get 4 phases in invariant reactions, and they are on horizontal planes. So here's our composition grid. On a binary, you just read across the bottom, but on a ternary, we have this composition grid, okay? And we've got our components at each corner, and imagine lying this down, and then the temperature is going up the side, going up vertically, just as it does on a binary phase diagram. Here is reading compositions. What you do, say we want the composition of A, you go to the other side, and then you count back from the other side to A. You're doing exactly the same in binaries, except it's just 1 straight line. So for this red X, we count back towards A, and it's 20, because on here, each little one is 1, and each solid line is 10. And then next thing we want to know is how much B is in there. So we go to the side opposite B, you count back 10, 20, 30, 40, 50. Now you could do how much C is in there by difference, but I always recommend that you work out C as well, because that will check that you've got everything right, because you know these add up to 100. So to work out how much C, you go the other side and count back 10, 20, 30. And then the purple X is just another one. So this one is 40% A, 10% B, and 50% C. Okay, So that's pretty important. Now, this is a space diagram of a whole system. It's not a very good copy because I've never been able to find a good copy. And you've got three, well, you've got more than that actually. You've got these planes, horizontal planes, and these are the invariant reactions. Okay. Now, this is very, very difficult to work out what's happening. And even if you can recognize the iron carbon diagram here and the chromium iron diagram there, it's very difficult to see how far back are you. Okay. So therefore, we try and do things to this to make it more two-dimensional. And you can look down on this and get the projection of the liquidous surface. You can have other projections as well, but that's the most useful. Or what we're talking about today is you cut a slice in there for a given temperature. So it's got to be a horizontal slice. And then you have an isothermal section. So this little diagram just shows, and it's for different systems. I just chose nice diagrams, but it just shows these various representations you can have. So first of all is the space diagram. That's the whole lot, but it's very difficult to interpret. Then we can have the liquidous surface looking down on it, and that's the topic of another lecture, and that's an example liquidous surface. Don't worry if it looks funny. Then you have the isothermal section, where you're cutting a horizontal section on it. So it's all at the same temperature. So it's in equilibrium. So this is an example isothermal section. And the other one we can have is a vertical section. And I'm not going to talk much about those because I don't like them. But here's an example. And the reason I don't like them is that the tie lines, and you'll find out in a minute what a tie line is, don't lie in the same plane as that. So although mathematically this is a vertical section cutting through there, it might not necessarily tell you how things solidify. And I hate these because people like to have them because they think it makes it simpler, but they can be misleading. Okay, so we're going to talk about isothermal sections. So there's our space diagram again, and here's an isothermal section showing you where it was taken, and there it is drawn there. So you've got liquid over here and solid over there, and between them you've got a two-phase region, liquid plus the solid alpha, our first Greek letter. And then you've got these lines on there, and what they are joining is phases that are in equilibrium with each other, or conjugate phases, and we call them tie lines because they are joining them that. So you will only find tie lines in a two-phase region or a three-phase region, but we're not doing that at the moment. And then down here was cutting lower, an example, okay? And we've got tie lines, and notice they sort of fan out from each other. So, and then the last section is cut here, and it's pretty boring. It's all solid. So we've already seen these tie lines, and what I want you to pick up is that the tie lines are all going in different directions, and they fan out, you see, pointing back towards the solid. And here they fan out in a different direction. Okay, don't worry about that too much. So my point is here, if you have a vertical section, is it going to, how likely is it that you're going to get all the tie lines right over all the temperatures? You're not. Okay, and that's why I don't like vertical sections. This just goes back again. We've already looked at this, but what you can have is you can on an isothermal section, which is useful because it's all at the same temperature, so it's all at equilibrium. And what you've got here, this shows you constant A, and this shows you a constant ratio B to C. This is quite useful because if you've got this plotted in atomic percent, you can see that this is going in at the same direction if a phase was lying along that line. Here's now, normally, if you're looking at, if you're interested in all the components equally, you have an equilateral triangle. But sometimes you're only really interested in one component. And then what you do, you use a right angle triangle, and it's usually truncated. So here's a little example showing the right angle. Here's a real example, and this is a triangle, but it's truncated. It's been cut off. Carbon only goes up to 9%, okay? And we're really interested in the iron-rich corner, and we're also interested in what happens in chromium, but we're not really interested in what happens with carbon. And so what we've got here is we've got some single-phase regions which are labeled. These are also single-phase regions, but they're special cases. And what's happening here is this, we call them line compounds because they form a line. Basically, they have very little solubility difference that way in the carbon and the metal. But what happens is that they do go in because in this case, the iron is substituting for some of the chromium. Okay, and here again, the iron is substituting for some of the chromium. And in this example down here, Fe3C, the chromium is substituting for some of the iron, but you still have exactly the same proportion of carbon in each of these phases, and they never change. And then we have two phase regions between the single phase regions, and where the single phase regions, what you can have is you can have three phase regions between single phase regions. So here we've got gamma iron joining up with Fe3C, joining up with, it's called Cr7C3, but it's actually, you quite often see M7C3, M to denote metal. So this is a three-phase region. So on the corners, it joins single-phase regions, and on the edges, it joins two-phase regions. Okay, there's something else going on here. It's a bit incomplete. So here we've got another three-phase region. Here is a two-phase region lying between the three-phase regions, and this is a two-phase region here on the side of the three-phase region and lying between the two single-phase regions. Here's another two-phase region lying between this single-phase region and that single-phase region, and also lying between the two three-phase regions. And finally, this is a two-phase region lying between here and here. So that's a nice example, but it's not very annotated. This is a more normal example where it's got lots of nice annotations on. And I've tried to help by showing you the phase fields. Some of them are already annotated. And how you would read this is you would obtain the system that you're interested in at the temperature you're interested in, or as near as possible. If you've got a program like Thermocalc, you can calculate it for exactly. And then you've got this isothermal section. You've got the temperature that it's for. It's useless unless you know what that temperature is, but you can, if you don't, and sometimes you see them published without the temperature, you can match them up against the binaries on the outside to work out the temperatures. Right, so this is a single phase chromium. This is, like it says it is, the chromium solid solution. The brackets are to show it's a solid solution, and beta down there. Notice it's lying between those two phases, and also notice that it's got two three-phase regions on either side. This is a three-phase region between chromium, where that corner meets, gamma, where this corner meets, and beta, where that corner meets. And you'll notice on each side, it's got the two-phase regions. We've done all those. There's beta. And this phase diagram is actually wrong because it's calling this aluminium. And it's not aluminium, it's actually liquid based on aluminium. And it should really be liquid, okay? Because aluminium melts at that temperature. They always quote it to three decimal places, which I think is strange, but I'll go with the flow. So at 1150, it will be melted, and this should be liquid. Here's another example. And what this shows is, you know what I said about matching it up? Well, this tells you it's at 500 degrees Celsius. And what we've got is the 3 binary phase diagrams. And this whole story has to be consistent. And this is an isothermal section at 500 degrees C. And you could match it up. This would be the easiest to match it up at. Well, you could choose any. But if you look along here, you've got a large liquid region, and there's that large liquid region. Then you've got a 2-phase region between the liquid and Ag2Te. There's that 2-phase region, well, there. And then you've got a 2-phase region between that intermetallic and the solid solution of silver. Okay, so it matches up, it's consistent. This one is similar. At 500 degrees, you've got that much liquid. There it is. And then you can follow across the phases. So it must match up. And here again, you've got a little bit of liquid there. You've got a 2-phase region between liquid and cadmium tellurium rather. Then you've got cadmium tellurium itself. There it is, a single-phase region. And then you've got another 2-phase region, and the liquid comes, yeah, it's difficult to see. The liquid does come down there because it's showing it there, okay? Must all be consistent. So there's a single-phase liquid. There's a single-phase field, silver 2 tellurium. There's a single-phase field, silver. It doesn't go in very far. Then we've got silver cadmium. I can't read that much too much, but it's another intermetallic phase, as is there, and then liquid. And then you've got these 3-phase fields, which are just empty triangles, if you like. And then where the tie lines are, you've got they show the 2-phase fields, okay? So you've got 1, 2, 3, 4, 5, 6 ternary, or 3-phase fields rather, and each of them joins up to a single phase, okay? All of them do. And then you've got the 2-phase regions between the 3-phase regions, and also between the single-phase regions. And it's got to be consistent. And in fact, what I'm going to do is I'm go back a bit. If I put a line across here, and I'm not going through the points, I'm going straight across here, the numbers of phases as you go along that line will change by 1. And the phases themselves, their names, will also change by 1. So we'll call this liquid because that's more correct. So we've drawn a line across there just to make it a little bit more easy for myself. So we go liquid plus gamma here. So we got 2 phases, liquid plus gamma plus beta there. Then 3 phases, then gamma plus beta back to 2. Then gamma plus beta plus chromium up to 3, chromium plus beta back to 2, then chromium plus beta plus nickel-rich solid solution back to 3, and then we cross into here, chromium-rich solid solution and nickel-rich solid solution back to 2. And if it doesn't work like that, then either the diagram is wrong or you've miscalculated somewhere. You've interpreted it wrong. Sometimes what you can have is you can have 2 3-phase regions which are very close to each other because there's very little solubility difference between the single phases. And I haven't got an example of this because we have got a solubility difference, but you can have that. And then you have the 3-phase triangles actually abutting. And in those cases, you seem to go from 3-phase to 3-phase, but that's because the 2-phase region between them is very, very narrow. Here's a nice example, nice and clear, where it's calculated, and it's calculated using MT data, which is one of the programs. And here's a single phase region. Here's another single phase region. here's another single phase region, and here's another single phase region. And then what they've done is they've calculated it, and they've also put on some experimental results to see how well they agree. And you can see that this is wider in the calculation than the experimental results. Okay, so you've got two phase regions between the single phase regions with the tie lines, another two phase region, another two phase region, another two phase region. And then between the two phase regions, you've got a three phase region. And notice you've got the same pattern, that the three phase region is meeting a single phase region at each point of it, or each vertex. Okay, all got to be consistent again. Here's another calculation, and it's more complicated. What you've got is this massive single phase region going along there. Okay, and then you've got loads of three phase regions, okay, shown by the red triangles, and two phase regions between them, and the shape of them is because this hasn't got very much solid solubility in the calculation. So these phases along here, these single phases along here, don't have very much solid solubility in the calculation, so they're not going in very far. Okay, and then the green is showing the tie lines again. And there was a bit of a mistake. Well, basically what happened is we had to put separate compositions sections down, and we sort of ran out of steam here. Okay, and I think that's it. Thank you very much. And I can't stop recording.